Okay, this is our last topic related to RC circuits. Well, we're going to do RC circuits a bit later when we do AC circuits, alternative current. But here with circuits with batteries, the last topic with RC is the topic of energy. So actually, what I'm going to cover is mostly things that you already know, but I'm going to also get a new equation that will be very useful when we talk about energy in those circuits. So how do we get energy? How do we calculate energies in circuits? Well, we do it through the power. And remember the power in a resistor, for example, we have three equations for a resistor. We can use either P equal Ri square, or using Ohm's law, you can replace I by delta V over R. So if you replace the I by delta V over R, you get that the power is also delta V R square over R. Okay, by delta VR here, I mean the voltage across the resistor squared over R. Or we can also use the current times the voltage across the resistor. And here I take an absolute value because I want the power to be positive. But what's the meaning of that power? That's the energy per unit time per second that is dissipated in the resistor. So it's energy that goes away, that is taken from the charges and given out of the circuit in the form of heat or light, if you have, let's say, a light bulb. Okay, so that's the energy taken away from the circuit and transfers out to the outside world in the form of heat or light. That's the power in a resistor. For a battery, we cannot use any of those equations, but we have to go back to, we cannot use this one or this one for a battery here because we have no resistance. I'm talking about ideal batteries. But we can use this equation for a battery here as long as for delta V we use the voltage across the battery, which is what we call the EMF. So for a battery we use the power is just I times the EMF. And that's, of course, the current that flows in the battery. Okay, well, we can use that for a charging or discharging battery. If you calculate I times E for a charging battery, that means it's energy taken, energy per unit time, energy per second, taken away out of the circuit and transferred to the battery. If the battery is discharging, then this is energy given to the circuit by the battery. Okay, what about capacitors? Well, when we have RC circuits, first of all the equations I just wrote are still valid. The only difference is, of course, that now we have things that are changing in time. So the current is changing in time. Therefore, when you use a power, you can use R times I square, but the current flowing through the resistor is changing with time. So it's a function of time. So the power dissipated in the resistor is also a function of time. You can use the other formula again, but again, the voltage across the resistor will vary with time in the RC circuit, or you can use the current times the voltage across the resistor, but again, now the current and the voltage are functions of time. For the battery, you also have a function of time. The EMF is a constant, but the current flowing in or out of the battery is a function of time. So to get the power, that is a function of time. Okay, so this is all old stuff. Now we want to talk about a capacitor. For a capacitor, what do we use for the formula of the power in a capacitor? We use the current times the voltage, but of course we use the voltage across the capacitor. So the current flowing in or out of the capacitor times the voltage across the capacitor gives the power of the capacitor. Okay, and we take an absolute value here because I want the power to be positive. But what does this power mean? Okay, it's the power in watts, but what do we mean by the power of a capacitor? Well, the meaning is a bit different if we talk about a charging circuit than if we talk about a discharging circuit. So let's look at the charging circuit. The basic circuit is the battery here, capacitor, and a resistor. And we've closed the switch at t equals 0. So what happened? We usually start with a capacitor that is initially on charge, and you close the switch so the charge starts to accumulate. In this example here, this is the positive terminal here, so the current will flow that way, and you're going to accumulate positive charges on this plate here. So if you calculate I of t and you multiply by delta Vc, you get the power. But what does it represent in this circuit is energy that is being stored in the capacitor as it is being charged. So we're charging the capacitor and we're storing energy in the capacitor. In what form? Well, the energy is stored in the form of charges that are piled up here, positive charges on this side and negative charges on this side here. So you're piling up charges there, and they contain potential energy. So this power is the energy per second that is being charged in the capacitor, being stored in the capacitor. Okay. Now, in this circuit, conservation of energy would say that, so you see the battery here is giving energy to the circuit, and that energy goes into the capacitor, is being stored in the capacitor, and it's also dissipated in the resistor in the form of heat or light. So conservation of energy, or using power here, tells us that the power of the battery here, that's energy given by the battery to the circuit, should be equal to the power in the resistor, energy given away, plus power stored in the capacitor. So we should have this equation here. And this equation is always valid for a charging circuit. If you have a discharging circuit, the meaning is a bit different. What's the power of the capacitor? Remember the setting. We had a capacitor that is now initially charged, because if it's uncharged, nothing will happen. So we start with a charged capacitor. We have a switch. We close the switch. The capacitor starts to discharge. So in this example here, if this is a positive terminal here, you'll have a current flowing this way, and you have a current flowing this way here, and you have positive charges that are moving this way. They move here, they cancel the negative charge here, and eventually all the charges would have left the positive plate of the capacitor, and the current will stop, right? All the charges would be transferred from the positive side to the negative side, then there will be nothing going on anymore, and the current will stop. So in this circuit, we start with a charged capacitor, so there's energy stored in the capacitor at the beginning, and as time passes on, this energy is transferred from the capacitor to the resistor, and that energy is given away in the form of heat or light. So the source of energy here is the capacitor, and the energy goes to the outside world through the resistor. So in this circuit here, we expect that the power in the resistor, that's energy taken away from the circuit, must be equal to the power of the capacitor, because the capacitor is giving energy to the circuit. So we have this equation in the discharging circuit. Okay. Okay. Now, just a reminder: what is power? Power is a rate at which energy is given away or taken by a circuit element. So by definition, power is the derivative of energy with respect to time. That's the fundamental definition. Okay. Now, once you have this equation here, we can isolate dE. So I just move dt on the other side, so I get this. dE is power times dt. Now, if you want the energy, total energy that is, let's say, stored in a capacitor or dissipated in a resistor between two times, what you want the total energy, then what you have to do is that you have to integrate. So what we're doing here is that if you integrate dt from a time, dE from a time t1 to a time t2, the meaning of this side here, that's the total energy that is stored, let's say, between the time t1 and time t2. And on the other side, you integrate this. So the integral of dE just gives you energy, and on the other side, you're left with the integral of p dt. Again, what's the meaning of this? Let's say you have a certain power in a resistor, for example. You integrate the power in the resistor between T1 and T2. What you get is energy. That would be the total energy that was dissipated in the resistor between T1 and T2. If you integrate that for a capacitor between T1 and T2, that could be the total energy stored in the capacitor between T1 and T2. So this is the basic definition for energy. You integrate the power times dt. Now, then what you do with this integral here depends on whether the power is a function of time or not. If the power is not a function of time, then in that case, p is a constant. You can move it out of the integration sign. You can move it outside, and then you can integrate dt. The integral of dt is just t, and then you evaluate it between t2 and t1, so you get the energy is p times t2 minus t1. Okay, this is the energy you get if the power is a constant in time. But in our RC circuits, power is not a constant of time. So basically, this is the equation you might have seen in mechanics. Energy is the power times delta T. But this is true only if the power is a constant in time. In our circuits, power is a function of time, so we cannot use this form here. Okay. Just to look at a specific example, consider a capacitor that is being charged. Okay, so we start, let's say, initially on charge, and we connect it to a battery and a resistor. Okay, and we wait until it has accumulated a total charge, let's say QF. So I wait until it has reached a certain charge QF. It might not be totally completely charged yet, but okay, I start at t equals 0 when it's on charge, and I wait until it has a charge QF. Now, what's the total energy stored in the capacitor? It will be the integral from t equals 0 from the beginning until a time tf, that's the final time, when the charge, tf here, I mean, this is the time, the instant at which you have a charge qf on the capacitor. And I integrate p of t. Okay, now we're going to do this integral. And we're going to be totally general. So what is p of t for a capacitor? P of t is the current times the delta V across the capacitor. So I can write it this way. That's the energy stored on the capacitor between t equals 0 and t equals tf. So it's equal to this. Now remember, for a capacitor, delta Vc is given by Qc over the capacitance. And the current for a charging capacitor is just dQc dt. So we get this equation here. So all I did was to replace delta Vc here by Qc over C, and the current here I replaced by dQc dt. Okay, now that's the energy. Notice the dt here, I can cancel them out. So that drops out. The capacitance is a constant, right? It's not a function of time, so I can move it outside of the integration. So I get this. Okay, I just rewrote the equation here, and then I get this. Okay, so again, what I did was to cancel the dt here and to move the 1 over c outside. I get this. Now this integral now is a function of time, but notice it's rewritten in terms of the qc variable. So you have qc here, which is a function of time, times dqc. So what we can do is that we can forget about the time here and just think of that as integral over qc. Okay, qc is a variable, and you have dqc. So forget that, don't write the time dependence here for a second, write that like this here. And because now we're focusing on the variable qc, we integrate from t equals 0 when the charge is 0 until tf. What's the charge when you reach a time tf is what we call qf. So now we have an integral over qc. That's our variable. So this integral here, if it bothers you, qc is just a variable. So think of qc as being x, and dqc is dx. So basically we're integrating x dx. You know how to integrate that. So the integral of x dx is just x squared over 2. In our case, qc stands for x. So the integral of qc times dqc will give us qc squared over 2, which we'll have to evaluate between those two limits here. So we get 1 over c times qc squared over 2, evaluated between 0 and qf. So you plug the value q, and by qf, I mean here that you replace qc by qf, and then you subtract when qc is equal to 0. If you do that, you get this. Okay, so this basically I took this expression here, I replaced qc by qf, and then I subtracted with qc replaced by 0. So it just gives that here. And that's it. That's our key equation. This is the total energy stored on the capacitor between t equals 0 and until you reach a point where there was a charge qf. So that tells us that when you have a charge qf on a capacitor, it has an energy equal to q squared over 2c. So I draw the f here, and because the charge can be any value here, so I call that qf for my integration here, but you can just rename qf just q. And that gives us the key equation, which is that the energy stored in the capacitor, which has a charge q, so q can be anything, is given by q squared over 2c. So if you have a capacitor and you know the charge, this is always the charge on the positive plate. If it has, let's say, 5 coulomb on the positive plate, then you take 5 coulomb squared divided by twice the capacitance of the capacitor. That will give you how many joules of energy is stored in that capacitor. Okay, we can of course rewrite that in different ways. Remember, for a capacitor, Q is just a C times delta VC. So you can also write it this way. I just replaced one of the Q by, no, Q is just, Q for a capacitor is just equal to C times delta VC. So that's all I'm using here. Okay, this is always true at any time. This is the voltage across the capacitor times its capacitance. You can replace Q by this. If I replace this Q by C delta VC, I get this here. If I replace this Q here by C delta VC again, I get a third form here. Those are, so if you know the voltage across the capacitor at a given time, it's, you know, it's 5 volts. You square that, divide by 2, multiply the capacitance in farad, and then you get the energy in joules. That's the energy stored in a capacitor. Okay, so those three equations are equivalent for the energy stored in a capacitor when it has a charge Q, or when it has a delta V, a voltage across the capacitor, delta VC. Okay, those are important equations. As a test, just a test of that we understand things correctly, consider now a discharging circuit. Remember what we do, we start with a capacitor that has some charge Q initial. So we start some charge here, we close the switch, there's a switch here that I close, and then the capacitor starts to discharge. Now, obviously, all the energy stored in the capacitor would be dissipated in the resistor in the form of heat or light. So we must have conservation of energy. All the energy stored here must end up being dissipated in the resistor. We should check that. We know the energy stored here from the previous equation. The previous equation tells us that the energy stored here, if you have a charge Qi, and let's say here, okay, I didn't write it here, but let's call C the capacitance of a capacitor here. So let's say C is known. So if I tell you the charge Qi on this capacitor, and I give you its capacitance, you know the energy stored there is 1/2 Qi squared over C. That's the energy stored here. Now we close the switch. All the capacitor will discharge through the resistor, so all that energy must be transferred to the resistor. We should check that. Remember, for a discharging circuit, just a reminder, the current as a function of time was given by this equation, decreasing exponential, with I initial given by Qi over RC. We saw that earlier. Okay. Now, what's the power in the resistor? The power in the resistor is just, you can use that form, R times I squared. And we know the current here is a function of time. So we know the power in the resistor is given by R times this function here squared, with I sub I given by this. Now, what's energy transferred? The total energy transferred to the resistor as you let the capacitor discharge completely. The total energy transferred to the resistor should be the integral from t equals 0 to t equals infinity of the power in the resistor. So it should be equal to this. Okay. Now we can calculate that. So it's given by this, but you know that this is given by Ri squared. So plug Ri squared here, plug the I of t that we just gave before, do the integral, and you should get this, which is exactly what we expected. So when you integrate this, you should get this value here, and that proves that indeed all our equations are consistent. What we have shown is that this integral here gives this. This integral here, what does it mean? It means the total energy that was transferred to the resistor between t equals 0 and t equals infinity. But that energy came from the capacitor, which was initially charged with the charge Qi. So the total energy transferred to the resistor, given by this, should be equal to the total energy that was stored in the capacitor at the beginning, which is given by this. And indeed, when you do this integral here, you should get that. Okay, I'll let you try that, and that's a very good exercise. Thank you.